This is EC 201, lecture 36. So in the last class, we looked at a differential pair with an active load. What we said was this is the so-called active load, and we derived this from scratch. The motivation in having the active load is pretty much the same motivation we had when we were discussing common source amplifiers and common emitter amplifiers, where we realized that if you have a resistive load, to get a large gain you need a very, very large supply voltage. Because if the supply voltage is small and you want to get a large gain, then you would have to increase the resistor, which would push the input devices. What are the input devices called in this case? So if the load resistors were too large, then the output voltage when Vd was 0 will be of the form some VCC minus I0 times R, and if you wanted a large R, you would increase R, make larger and larger and larger, which would eventually cause what to happen? It will push Q1 and Q2 into saturation region where all your active stuff, all your voltage controlled current source is not valid anymore, so you will not get any gain. And in the case for common source amplifier, we mitigated that problem by putting in what is basically a current source, and the current source is realized using a transistor operating in the active region. And we realized that you have a PMOS common source amplifier. The right thing to do is to put a current source sucking current out of the drain of the PMOS transistor, and that was realized using an NMOS transistor. If we had an NMOS common source amplifier, then you would put a PMOS current source, and the same thing holds for the bipolar too. In this case, for example, if we restrict ourselves only to using NPN and PNP transistors, if you have an NPN pair giving you the gain, then the load must be a current source, and the current source must be pushing current into the collector of the NMOS transistor, alright, and that is basically a PNP transistor. And then we notice that instead of having a current mirror with separate current biasing the other end of the mirror, we could actually hook it up to the collector of Q1 where that current I0 is always available. And then we said, let's take a look at the small signal properties of this amplifier. For analysis sake, make the following assumptions, which are, let's neglect betas, so all betas are infinity. The only reason I am choosing infinity is because it's quicker to analyze in class. You should be able to analyze it with a finite beta. Then, whether this is an NPN transistor or a PNP transistor, all the betas are infinity. Then, again, as I said, for simplicity, I will assume that the NPN devices have VA equal to infinity. What is VA? The early voltage. What is the implication of having an infinite early voltage? The IC versus VCE characteristics are flat when the transistor is operating in the active region. In other words, it behaves like an ideal voltage controlled current source for incremental signals. Let's say the PNP devices have a finite VA, and this results in an output impedance, say R0. Under these assumptions, can we draw the small signal equivalent of the differential pair? And VCM is a bias quantity, capital VCM. So the input becomes small Vd. The small signal here becomes minus V sub D. What happens to the current source? I am trying to draw the incremental equivalent circuit of this guy by replacing element by element with the incremental equivalent. So what happens to the tail current source? Open circuit. Okay. What happens to this chap? VCC? Ground. Can we actually use half circuit analysis here to simplify our calculations or no? No. Why? The circuit is not symmetric anymore. But thankfully, because of the assumptions I have made, You can actually do it for some part of the circuit. I'll show you how. I replace now every transistor with its incremental equivalent. What is the incremental equivalent of Q1? Please note that we have assumed beta for the NPN transistors to be infinity. If this small signal is Vx, this must be Vd. What must be the strength of this current source? Gm into Vd minus Vx. And please note that even though the input excitation is purely differential, I have not made the emitter coupled node incrementally ground. I have called it Vx. Why is this justified? We have not assumed symmetry, which is why I cannot make Vx 0. Alright. Then I replace this chap by the corresponding small signal equivalent. This must be Gm times, this is minus Vd minus Vx. Great. Alright. Then my next job is to replace every transistor, the PNP transistors, with their incremental equivalent circuits. What is the incremental equivalent circuit of the PNP transistor now? What is the strength of this current source? It is this transistor I am interested in. That's this guy. This current source must be controlled by the incremental what voltage? Base emitter voltage. Okay, so we need to actually name this, let's call this Vy. So what should the current source strength be? Gm Vy. Alright. Is that all, or is there something else? I need to add an R naught in parallel with the current source. The last thing I need to do is replace the other transistor with its small signal equivalent. What do I do there? There is R naught. There is the voltage controlled current source. And what is the strength of the voltage controlled current source? Gm times what voltage? Vy. Why? Because both these transistors have the same base and emitter voltages. Now, what all do we need to find? We need to find, obviously, our interest is in finding the incremental output voltage, V out. Isn't it? So now can you help me figure out how will I go about finding V out in terms of Vd? Okay, what all unknowns do we need to find? We need to find Vx, Vy and V out. So would you go about finding Vx first or Vy first? Vx, why? The Vy is being generated by some current which depends on Vx, so it makes sense to find Vx first. Alright, and so what is Vx? No, incremental node voltage Vx must be 0. Okay, if you didn't realize that it is 0, how will you find it? You just write KCL at this node. Okay, one nice thing about Kirchhoff's equations is that whichever way you come to the solution, if the solution satisfies the equation, it's a legal solution. So if I assume Vx is 0, what happens? This current is equal and opposite to this current, and that satisfies Kirchhoff's current law at that node, so Vx is 0 is correct. A more formal way of doing it would be to write the Kirchhoff's current law at this node. Is that clear? So once Vx is known to be 0, I just connect this to ground. This becomes GMVD. This becomes minus GMVD. Alright. and I can get rid of these guys just to reduce clutter in this diagram. I need to find V out now. Incremental Vy is found by writing KCL at this node, but intuitively it is seen that this chap here looks like a resistor of value 1 over Gm in parallel with R0. So that's very good. So Vy must be straight away minus Gm Vd times 1 over Gm parallel R0. Is that clear? And can you comment on the relative magnitudes of 1 over Gm and R0? R0 will be much larger than 1 over Gm. So this quantity is going to be approximately equal to, if you parallel large resistor and small resistor, the equivalent resistance is the small resistor itself. So this is approximately 1 over Gm, okay, which implies Vy is approximately equal to what? Minus Vd. Okay? You understand? Alright? So if, and I mean the reason why we made this approximation is not to carry this 1 over Gm parallel R0 everywhere. Is no big deal, I mean. Okay? Now, what is Gm Vy? Vy is minus Vd. So, I can replace Gm Vy by minus Gm Vd. Alright? So what is incremental V out? It is 2 Gm Vd times R0. Does it make sense? Please note that the total current flowing out of this node is 1 GMVD this way, another GMVD this way, alright. So the total current flowing out is minus 2 GMVD, which is equivalent to saying that the total current flowing into this node, in the small signal sense, is plus 2 GMVD. That multiplied by the resistance at that node should give you the incremental output voltage. So V out is nothing but 2 GMVD R0. In other words, the small signal gain is what? 2 Gm R0. You understand? And clearly, as R0 tends to infinity, what will you get? If R0 tends to infinity, what happens to the gain? The gain also goes to infinity. Okay, that's what we expected anyway when we did the active load for the common, the common source amplifier. All right, and as I said, all this calculation, this 2 Gm R0 is only valid when all the transistors are in their active region. Okay. So if the gain is very large, what does it mean for the potential at this node? Okay, originally Vd was 0, okay, and now the gain from here, from Vd to the incremental gain from Vd to the output is very large. So a small change in Vd will result in a very large change in the output potential. Okay. So basically what are we seeing? If Vd is positive, even by, let's assume Ro is infinity, so that the gain is really infinity. So even a infinitesimally small VD plus positive VD will result in this potential going to, if VD increases, what happens to this potential? Will it go up or go down? The incremental gain is positive, so if I increase VD, the output incrementally increases, albeit by a very large amount. So if VD goes up, the output will also go up. Okay? And if this node potential goes up, what happens? If this node potential goes up and up and up, what will happen? It will push. Come on guys. If this node potential goes up and up and up, eventually it will go and push this transistor out of the active region into its saturation region, causing the gain of the amplifier to fall. Okay? Does that make sense? Alright? Similarly, so what is the maximum voltage here that will still keep this guy in saturation? What is the maximum voltage here that will keep this chap in saturation? It is simply VCC minus, let me just, let me call this Q3 and Q4. This is V out. So if V out goes too high, it will push Q4 get saturated. On the other hand, and how high can V out go? V out maximum is, what is it? VCC minus 0.65 volts. VC sat, which is 0.65 volts. Is that clear? On the other hand, if V out goes too low, what happens? If this potential goes too low, it's going to crush this device. So, what is V out minimum? What is it? How low can V out go before pushing Q2 into saturation? VCM minus? VCM minus VD. As long as this potential doesn't go lower than the base, you're okay. And we know that VD is very, very small anyway. So V out minimum is simply VCM. Alright? So, okay. So the range of potentials possible at V out, okay, which will still allow the transistors, all the 4 transistors concerned to be in the active region so that you can get a large incremental gain, is VCC minus 0.65 volts and VCM on the lower side. So in other words, now based on this knowledge and the fact that the gain is very, very large, if I plot VD on the x-axis and the quiescent potential V out, I mean the potential, the absolute potential at V out on the y-axis, Can you tell me what happens? Assume R is infinity, so the gain is very, very large. If VD is even slightly positive, what happens? What will happen? The gain falls off. Okay, because even if V out is infinitesimally small and positive, the transistor, which of these transistors is in trouble? Q4 gets into the saturation region, thereby causing the gain to fall off. Okay, so if the I versus V, and at VD equal to 0, the gain is very, very large. So okay, so the infinite slope region is bounded on the top by what voltage? VCC minus 0.65 volts. Okay, and it is bounded on at the bottom by VCM. And beyond this point, the gain will become small. So it probably does something like this. Alright? And unlike in the MOS case, we can't really, based on the knowledge we have so far, where I have not discussed the properties, the exact IV characteristics in the saturation region, it's not possible to predict what the behavior here is going to be. Alright? Only thing we know is the gain is smaller. Alright? Okay, in the bipolar case it's a little more tricky because it turns out that when the VCE is very small, there is actually current flowing from when the transistor becomes saturated. In other words, the collector goes below the base, there is a significant part of the base current actually now gets into the collector also. Okay, making the analysis a little painful, so which is why I avoid it. In any case, as op-amp designers, you want to avoid that. You do not want the transistor to get into, any of the transistors to get into saturation. And like all high gain amplifiers, okay, even if you breathe on the input, you basically see that it's impossible to keep the output. It's impossible to keep the output on this characteristic because the slope is infinity. Even if you breathe on it, it will either go here or here. Okay, which again reinforces the idea that you cannot operate what? You cannot operate a high gain amplifier in open loop. Okay, it is negative feedback which will go and force everything to behave. Alright, does it make sense? So, okay, so now that so this is exactly the differential analog of what? This is the differential equivalent of what we have done earlier, and what is that? When we first introduced the active load, we said we have a PMOS transistor with a current source in the drain. Okay, and there also when you plotted the input versus output characteristic, you find that there is a very, very sharp slope, and then beyond below that, and for inputs below what gives you the sharp slope and inputs beyond that, the gain reduce. Okay, so this is exactly the differential analog of a common emitter or a common source amplifier acting, being excited with it's the differential analog of a common emitter or a common source amplifier with an active load. Alright? And as we have seen here, if the output, if the output impedance of this current source is infinite, then the incremental voltage at the output is given by 2 GMVD RO. In other words, the output of this amplifier, just like in the resistor case, is also not sensitive to the common mode at all. Okay? So this incremental output voltage at this node only depends on the incremental differential voltage. It is not sensitive to the incremental common mode voltage, because we have assumed that the output impedance of this current source is infinity. If the output impedance of this current source is not infinity, you have to plot along with draw the equivalent circuit, and you will get the same result, which is depends on the, you will get a common mode rejection ratio, right? And the common mode rejection ratio will be of the form GM times 2 RS or RT or whatever we called it. And as the output impedance of the tail current source becomes larger and larger and larger, we will find that the common mode rejection ratio approaches infinity. Is that clear? Okay, so let me now push on to the next case. Okay. So as we saw, this, if the ROs become very, very large, is capable of giving you an output voltage where the incremental output is a very large number times the incremental differential voltage. This is what the op-amp is basically trying to do. The question now is, are we done, or can I call this an op-amp? It has 3 terminals, 1, 2 and 3. Okay. The incremental output here is a large multiple times the difference between these two nodes. So, is this okay for an op-amp? Can I just put this inside a triangle and sell this? Or is there something I'm missing? Okay, if I do want to sell this, I want to label this as okay, so which must be the plus terminal of the op-amp? This, the base of Q1 is plus, this is minus, and V out is the output. So if I did this, what are the problems? First of all, can I do this? And 2, if I did it, what are the problems? Okay, that we understand, that when we sell the op-amp, we will tell the user, hey, look, you can't apply these 2 input terminals, the common mode of those 2 terminals must be within the common mode range, which are dependent on VCC and VEE. So if you fool around there, right, and expect the op-amp to work, tough luck. Okay, you should assume a reasonably intelligent user, not a donkey. Okay, all right. When you design software, you make sure that you design it for a donkey, but not for, okay, alright. So, well, why are they different? Yes. No, we can always express any V. I mean, please note that the gain is sufficiently large, right? We already let's assume that GM times R is fairly large. In which case, if the negative feedback loop is working, then we expect the difference between the two terminals to be almost zero. Okay, so the finite difference between these two guys is, not that much of an issue, isn't it? I mean, can you think of a simple op-amp application and see if this works? I mean, how do I know that this doesn't behave as an op-amp? What did I do? I would, I probably use an op-amp to make, some voltage control, voltage source, whatever, right? Or a unity follower or something. If it works, then perhaps this is okay, alright? You understand? I mean, if you got a black box, something which looked black and soft and somebody told you it's a cake, how will you figure out if it's a cake or not? Eat it, my God. Huh? You will give it to your neighbor, right? If the guy is still alive, then you know that it might be something, alright? And you eventually get through your entire hostel, and if everybody is alive, by the time the cake is over, so there's hardly anything you can eat. Okay? So basically, so if I gave you a black box saying this is an op-amp, what will you do? And I tell you, if it doesn't work as an op-amp, you get your money back. So what will you do? You will try and find counter examples where it doesn't work, it couldn't possibly work, and if it still works, then you know that inside is a really good op-amp. Okay? Alright. So the simplest circuit that you can think of is what? Unity follower. So let's see if this works as a unity follower. If it doesn't work, we know that there is already a problem. We've got to fix it. Correct? So with a unity follower, what do? We need to connect the output to the input like this. We will apply a sine wave here, and hopefully out must come a sine wave. Correct? So let me see, what should I do here? Connect V out to that's what this is. Right? The output to the output gets connected to the negative terminal. We identified this as the output, this is the negative terminal, so connecting the two should give me a unity gain follower. Alright? Okay, so does this work as a unity gain follower, or is there a problem? And we'll assume VCC is positive and VE is negative, so that when I put a sine wave here, 0 is inside well within the input common mode range. Okay. So does this work, or does this? What do I mean when I say does it work? When will it work? It will work this output will follow the input as long as the amplifier gain is very, very large. That only happens when all the transistors are in their active region. So as long as over the entire signal cycle all the transistors are in their active region, we are fine. Okay? That's what we mean when we say things work. So can you now help me figure out if this works as a follower or not? Pardon? Q2 is in the edge of active region, but it always remains on the edge of the active region. So that's not really a problem. I mean, what he's pointing out is that, hey, look, the collector and the base are shorted, so Q2 is at the edge of the saturation region. Perfectly valid, okay? But we notice that as the signal is changing, that remains, it always remains on the edge of saturation, so it's not a problem. What else could be the problem? No, it is no problem. I mean, many times it happens that there is no problem. Just because there is no problem doesn't mean that you have to get worried, right? You should be happy that there is no problem. So as the input signal changes here, what do you think happens at this node? Pardon? What will be the voltage here? No. What will this voltage be? I mean, I am asking you, this is a sine wave. What is this voltage going to be? Why negative? This is a unity gain follower. If the follower is working properly, whatever happens here must happen here. Okay? So this voltage must be the same as this. Okay? The question is, how large a sine wave must I put before things start to screw up? I think I will stop here. Please think about this. By the way, is it possible to meet tomorrow? We have a quiz. It's on Tuesday, right? So anyways, I want to discuss some problem sets. If you don't want to do it, that's fine with me. But if you want, I can come. Or do I make it optional and then, those who want come, that's fine. I will not take attendance. That's what you want. Okay, so tomorrow at 9 o'clock I'll be here. Those who want, the problem sets to be discussed, please show up. I don't know, I can spend, maybe an hour or a couple of hours without